So thank you very much to you all for getting up so early, 9 o'clock. I'm not sure it's worth it, but let's see. Then thank you very much for the invitation. It's a pleasure to be here for Olivier's birthday conference. Of course, new papers of Olivier, especially his little note on the counterexample to the global duality. But I think we actually met rather late. So my first visual memory of you is actually here. It's probably in the late 90s, asking Fabrizio for advice how to cope with back problems. Certain things never change. Recently, we've been interacting more, and I'm looking forward to continue this. Okay, so I'll talk about twistor spaces of K3 surfaces and certain mostly arithmetic properties of the fibers of these twistor spaces. I don't expect you to actually know what the twistor space is or not to remember it. So I'll start with a review of what the twistor construction actually is. Okay, so S will be a K3 surface over C. What I have to say actually makes sense, perfect sense for Hyperkähler manifolds as well. But just for simplicity, let's stick to the K3 case. And then, you know, the 2-0 part of its cohomology is generated by a non-degenerate form. Let's call it sigma. And then you can look at the volume form. If you just take the product of sigma times sigma bar, so that's a 2-2 form, so that's a top degree form on the K3 surface S. So that's in the sense of real differential geometry, that's a volume form. Okay. And then there's, of course, the celebrated Calabi conjecture proved by Yao that tells you the following. So for all Kähler class, so you give yourself a Kähler class, so that's certainly a 1-1 class. Kähler, there exists a unique Kähler metric. Let's call it G, having two properties such that, so the first property is of course that its Kähler form represents this class. So let's call the scalar form omega. So how do I get the Kähler form from the metric? Well, I just use the metric and plug in the complex structure in the metric, and that's a Kähler form, and this thing, Kähler form, represents the class alpha. So here I'm thinking of the K3 surface S as a differentiable manifold with a complex structure. Oops. So this is the complex structure I. Okay, so that's the first condition, and the second one is you want a comparison with a volume form. So you take another volume form you get in this situation, namely by just taking the square of omega. So omega is a 1-1 form, you take its square, it's a 2-2 form, and you want this to be sigma times sigma bar. That's maybe not possible, but you at least want to differ just by a constant. So that will be a positive constant. The constant is actually completely cohomological because it's given by the comparison of the intersection form of omega with itself and the intersection form of sigma with sigma bar. So here, this is my notation for the intersection form on the cohomology of Z. Okay. So this notion is transcendental. So this is a without making this too precise, one thing I could say that we have never seen any of those matrices. So no example explicitly known. In fact, you could think of producing natural Kähler metrics by embedding your K3 surface, at least when it's projective, into projective space, and then restrict the Fubini-Studi metric. And there's a result by Hulin that tells you that will never give you a Ricci flat metric. So if you embed your K3 surface S into some projective space, you take the Fubini-Studi Kähler form on the projective space, you restrict it to S. That will never be any of those omegas. There is, however, a result by Donaldson that tells you can approximate the Ricci flat metrics in terms of algebraic geometry. So suppose you fix an ample line bundle, so L ample, and you look at the embeddings given by the linear system, the multiples of n, of L, given by n times L. And then you can pull back, you can restrict the Fubini-Studi Kähler form to S for each little n. That gives you a Kähler form. By Euler, that's not a Ricci flat metric, but those will approximate appropriately normalized, will approximate the Ricci flat Kähler form corresponding to the Kähler class alpha, that is the first Schurian class of L. Okay. So now let's see, we can give a Hyperkähler interpretation of this Yes, there is a certain what they call balanced embedding of the. Yes. So the Hyperkähler interpretation is the following. So again, let S be our K3 surface, given by a complex structure on this real form manifold. And for simplicity, let's assume, I mean, we can always achieve this, that our omega square is just sigma times sigma bar. So by rescaling, we can assume the lambda is actually 1. And then we write this sigma, and we decompose it into its real and imaginary part. And it turns out both are also Kähler forms that come with respect to the given metric, but with respect to different complex structures. So, and this one is omega k. Okay, so J and K here are complex structures. But it's the same metric that is there. So what we observe is we know once we have this the K3 surface and we fix a Kähler class, or think of an ample class, then there's a unique way to get other complex structures J and K. So we have these three complex structures, I, J, and K, and they satisfy the usual relation between K, I, and J. This one. In fact, what you have is a whole sphere of complex structures. By just taking linear combinations of those three, and the condition to make this even an almost complex structure is that the triple ABC is contained in the sphere. Okay. So now from here on, thinking of the sphere as a complex P1, you get a complex manifold by looking at the differentiable manifold that you get from taking M times P1 plus the complex structure I that at a point X. So now the complex structure is an endomorphism of the tangent bundle, square minus 1. So the tangent bundle of the product is, of course, the direct sum of the two tangent bundles. So at the point X of M, and the point T in P1 corresponding to a complex structure like this, you say in the X direction, so in the M direction here, you take the complex structure given by T, and you take the usual complex structure on P1. And then this is a complex manifold. And you have a natural projection here, pi to P1, such that pi is actually holomorphic. So for instance, the original S, which was Mi, is one fiber, namely the fiber over the point 1, 0, 0. But you get other fibers, St for NET, and these are then all K3 surfaces for all T. Okay, so now you could ask, why is this interesting? Okay, there's more structure I'm not going to use. These twistor spaces, they come with twistor sections, so this pi has sections. So there are P1s in this S. These P1s, they actually deform in two-dimensional families. And roughly, if you give yourself a family like this, plus these twistor sections, these P1s in the surface, in the threefold S, and plus the anti-holomorphic involution, then this structure determines the metric G. So essentially no information is lost when you pass from the metric G to this twistor space. Okay, so the question is, why would you look at a thing like this? First of all, twistor spaces have always been used in the theory of K3 surfaces and also in Hyperkähler geometry. For instance, to prove surjectivity.
So the twistor family is as transcendental as the parageometric?
Yes.
So there's no explicit.
No. You see in a second why so there's no way of really writing down a twistor space. Like 30 years ago, there was a student of Burns, Topiwala, who tried somehow to approximate those three-dimensional twistor spaces by starting with something that is not a twistor space and then deform it a little. But there's no way of writing down the twistor space as such. So that's a good comment. So it's as transcendental as the G. So it's used to prove, for instance, surjectivity of the period map. To prove of the period map. Also, more recently, Pushkin used these twistor spaces extensively to prove the Hodge conjecture for certain products of K3 surfaces, S times S. I'll come back to this maybe later. In fact, there are ways to get around the use of twistor spaces. I think you could build a theory of K3 surfaces and also Hyperkähler without using twistor spaces, and you can also prove the Pushkin's result without using a Hyperkähler matrix, without using twistor spaces. But maybe that's not a good attitude somehow. Why? I mean, if there's a strong thing, why not using it? There is something interesting, so I hope to convince you. Okay. I think you can. So there's I haven't checked this completely, but there's a recent paper by Becker and Lehn where they look at singular hyperkählers and they prove surjectivity and things like this without using any twistor space, because somehow you don't have the notion of the metric. So that's and I think if you do this carefully, then you probably get everything without even for K3 surfaces and Hyperkähler manifolds. So. But that's not. I mean, that's not my point of view. You should not avoid twistor spaces. Maybe someone to give you. Yeah. So the question I've always been interested in is the following. So suppose you give yourself S. So this is one fiber of the family. What's the relation between this K3 surface and all the other surfaces? Okay, so I think there's in this general context, there's no way you can say anything reasonable. So you have to restrict, you have to make the situation slightly more algebraic by only looking at Kähler structures that actually come from ample line bundles. It's a bit like in this in these results by Ulan and Donaldson. So restrict to the case that omega is in fact something I call L. It's the first Chern class of an ample line bundle. Okay. So what do I mean by this? So here's an example. The second cohomology of S can of course be identified with the second cohomology of any of the fibers, because this S as a manifold, topological differentiable manifold, is just M times P1. And of course all the fibers are naturally identified. So there's really an equality, if you want, to H2 ST Z. The Néron-Severi group of S is of course contained in the cohomology, and everything that's orthogonal to the given ample class sits in here. So we have no way of predicting what exactly is the Néron-Severi group of the fiber, but we always know that it will contain this part. So here's the Néron-Severi, but we don't know what it is. But at least everything that's orthogonal to L will survive the process, and all the line bundles that have zero intersection with L actually define line bundles on all the fibers. So more general, because maybe let me mention this quickly, because it came up yesterday, the higher rank case, if you take a stable bundle, stable vector bundle, and for simplicity assume that its first Chern class is actually orthogonal to L, then there exists a natural bundle E, so holomorphic bundle on S, such that its restriction to the special fiber S is the bundle E. So it's really a natural construction. So you start with something interesting on S, and there's actually a way to extend it all over the twistor space. That's very interesting because, I mean, there are two interesting aspects here. So you have a family of K3 surfaces over a complete base. That's of course something very rare. You usually don't have families over complete base. And moreover, there's a way to drag information from one fiber to the other. And that's one example. And that's quite nice because that uses Hamid-Einstein connections. And you start with a stable bundle, then it has a Hamid-Einstein connection. You take the 0, 1 part of the Hamid-Einstein connection. That's the del bar operator for the holomorphic bundle E. But then you realize if you take the 0, 1 part of the connection with respect to any of the other complex structures, it's still a Dolbeau operator, and that gives you a holomorphic structure of E with respect to all the other complex structures, IT. Yes, so that's the easiest case in rank 2. Here there's, I mean, I should have said this, there's no, because for K3 surfaces there's no condition on C2. In higher dimensions you have conditions on C2, which you don't have here. And roughly this condition on the C2, so the condition Kieran talked about yesterday, is a condition on the norm of the connection that allows you, so for instance if you don't have this condition, then you can deform the projectivization of the E, and that usually is actually enough. Okay, so here there are two facts that are interesting and complement the pictures. The picture here. So if we start with our algebraic K3 surface S, and then we get this family of K3 surfaces, and most of them are actually just complex K3 surfaces. So if I take a very general point in the sphere, then the fiber is not projective. Okay. Now you could ask, what about those fibers that are projective? So look at the set of those which are projective. You see in the picture here, you see the Néron-Severi always has this negative definite orthogonal complement of L. So in order to make ST projective, you need one additional class that has positive square. So this set here sits in the set of all fibers with Picard number, at least the Picard number of S. So that's a set in S2, and that's countable and dense. Okay, so let's draw a picture. So here's my sphere. Then there's the point that corresponds to I. So this is the K3 surface S sits here, over here. maybe. So that's a sphere. I am. And then, if, for instance, you could take this complex conjugate, that would sit down here. Oops, M. I changed the order, I don't know why. M minus I. And then the set of those where the Picard rank is at least the Picard rank of the original K-thesis is a dense set in the sphere. Okay, so now you could be interested in that actually comes up in the set where the Picard group, and that can happen, is not only, the Picard number is not only at least the Picard number of S, but it's actually bigger. Okay, so if I look at all the T's in S2, such that the Picard number of ST is strictly bigger than the Picard number of S, this set is contained in the equator. So that's the equator I drew here. So outside of the equator, either you hit a non-projective K-thesis with Picard number rho minus 1, or you act K-thesis with Picard number equals rho of S. That still doesn't mean it's projective, but most of them probably will be. And then if you want higher Picard rank, those will always be concentrated along the equator. Okay. Well, it's a little lemma you have to prove. Maybe it becomes clear when I talk about the hot structure aspect. Okay, so now how will we study? So here you see describing line bundles on one fibers, and on the other fibers uses Hodge theory. And the only technique I really know how to study the situation is by Hodge theory. So now I go back a step, forget about twistor spaces for a moment, and tell you about the Hodge structure of a K3 surface, about the period and the endomorphism field, and then come back using the Hodge theory to describe the twistor construction. Any questions?
Isn't there sounds by Guillaume saying that in any small deformation of Hyperkähler, you have things where the Picard number jumps?
Yeah, I mean there's still jumps, so it jumps in this set of. See, the family you have is a one-dimensional family, and the Picard number jumps happen in the, so generically Picard number is rho minus 1, and the Picard number jumps in this dense set of points.
Okay. There you have.
But that's not a complex family. That's not a complex family. Here you have if you restrict to, I mean, so okay, so that's a family of K3 surface, generic Picard rank rho minus 1, and the point where it jumps is a dense subset. So that fits with the usual green, Voisin, Auguste. Other questions?
What is known about this set where this is actually projected?
In what terms? Like equidistribution?
Density? Because you said it's countable and dense on the right, okay, but...
Oh, you mean along the equator?
No, outside the equator.
So outside the equator is dense?
The small one is...
Both are dense, yes. Both are dense, yes.
And on the equator?
Yeah, so there my expectation is... well, I'll describe the equator in a different language, and then I'll come back to this. Okay, so let's talk about the Hodge theory. Okay, so again, S is our projective K3 surface, L is an ample class. And then the main structure we need is the transcendental lattice. Let me call it just T of S. So by definition, that is the orthogonal complement of the Néron-Severi lattice. And in fact, I only need so I don't need the integral structure, I only need the rational structure. So I put a Q here. So that's a Q vector space. Let's call its dimension R. So that would be, for the K3 case, it would be 22 minus rho, of course. And it comes with an intersection pairing that has two positive eigenvalues, and the other ones are negative. Okay, so this is some of the essential part of the hot structure, in the sense that the 2, 0 part plus the 0, 2 part of S is contained in the complexification. The real part of this this part here, which is a plane, so that's generated by the real and imaginary part of sigma. So if you want, that's omega j and omega k. This is a positive plane in the real vector space TR. So that's a positive plane. Okay. Also, we know that the T is an irreducible hot structure. And this tells you that if you use orthogonal projection, you actually embed the rational vector space in this real, and this is, so the map is injective. So that's orthogonal projection. So this is a vector space over R, that's a vector space over Q. So usually, so you can either embed T in P, or you can embed P in the real vector space TR. So usually, the T will not, the P will not intersect so this is a real vector space sitting in the real vector space you get obtained from this rational vector space by base change, and the intersection will be 0. So there will be no rational class in the real two-plane P. If not, then there are two cases. The first one is P is actually defined over Q, so that means this space here is of dimension 2. So that's the case if and only if P is in fact TR, or if you want for K3 service, that's the case if and only if the Picard number is maximal. And then there's the slightly strange case where the dimension is 1. So there are K3 surfaces, and quite a lot of them, where the positive plane, so which is a real vector space of dimension 2, contains one rational class and multiples of it, but it's not itself defined over Q. And there's no algebrogeometric description of those. Okay, and now there are two fields that somehow govern the situation. Yes, yes. So I'm always in this situation. Otherwise, I don't think I can say much. So somehow I make the situation slightly more algebraic. Okay, so now there are two fields we study. The first one is the period field. So you take the period of your hot structure. So you see, I mean, most of the things I'm doing have nothing to do with K3 service now. It just uses the hot structure T, which we call a hot structure of K3 type. So 2, 0 part is one-dimensional, and then there's this intersection form on it. So we take the 2, 0 part of the hot structure and view it as a point in the projectivized transcendental lattice, which since the transcendental lattice was over Q, this is in fact a rational vector space base changed to Q. Okay, so now that's a point in a projective space. You can look at its residue field, and that's what we call the period field. So that's the residue field. Explicitly, that means so we start with something over Q. We attach the coordinates, the affine coordinates of our period point x. So that's the period field. Then there's the endomorphism field. This is by definition, so that's capital S, that's the endomorphism algebra of the hot structure T. So this is the map, to make this precise, the map of Q linear maps, such that the PQ parts are mapped to the PQ parts. So it's slightly stronger than just saying 2, 0 is mapped to 2, 0, which would imply also 0, 2 is mapped to 0, 2, but you also need explicitly that 1, 1 is mapped to 1, 1. Okay, so then so this was really first studied by Zarshin, who explained that you naturally embed your endomorphism field, well, this endomorphism algebra, into C by taking a phi and mapping it to the scalar lambda, which is determined by the condition that on the one-dimensional space H20, which is preserved by phi, so it has to be lambda times the identity, and that's the scalar you associate to lambda. And by the irreducibility of the hot structure, that's really injective, and that tells you that that this Ks is actually a field. So more geometrically, you can think of as Ks. So you could look at the 2, 2 part on the product of the K3 surface S. Then there's a boring part that comes from taking products of divisor classes on the 2 component, and there's an interesting part that is the 2, 2 part of the transcendental lattice. So of the tensor product of the transcendental lattice with itself. And you can identify this endomorphism field with exactly this interesting part in the 2, 2 cohomology of the square of the K3 surface. Okay. Then you can prove the following. First of all, the endomorphism field always sits in the period field. So both are naturally subfields of C, so you can compare them. And the endomorphism field always sits in the period field. For the endomorphism field, you can say more, namely, so again, this is Zarshin. Its degree is always bounded from above by the dimension of the transcendental part. So in particular, it's a number field, whereas the period field satisfies a lower bound. And actually, usually, the period field is much bigger. I mean, you see, it's just the residue field of some point in this projective space, maybe in the period domain, and that's a quadric. But so usually, this is not even algebraic. Moreover, Zarshin explains that there are 2 possibilities for Ks. It could be a totally real field, so real multiplication. So that means for all embeddings, look at all the embeddings of Ks into C, they are actually mapped into R. Or it's a CM field, and this means it's an extension of degree 2 of a real multiplication field, so KS0 is real multiplication, and the extension here is quadratic and purely imaginary. That means it's given by the square root of an element here, which under any embedding is a negative number. So KS is KS0 times the square root of some lambda, and this one is I mean, it's a totally real negative number. Okay, so there are these two cases. So now you can define when a K-theta surface is called CM. So definition, so CM K-theta surfaces. So S is called CM. If, well, the first condition, of course, that the endomorphism field is a CM field. If Ks is CM, so then you're in the second case. But you want a little more. You want that you have equality in the inequality upstairs. So its degree is exactly the dimension of R. Remember, the endomorphism field was given as endomorphism of the transcendental lattice, so K acts on T. So T is a K vector space, and that means that as a vector space over T, over K, it is a one-dimensional vector space. Okay, and then you can prove a little proposition that shows you can actually characterize the CM K-theta surface in terms of the other field as well. So this is the case if and only if Ks is CM and of the correct degree, or you could simply say the two fields, so K, the endomorphism field sits in the period field, they are the same. So the CM case is the one where there's no difference between the two fields. So maybe I should say the very general K-theta surface will have will have real multiplication, actually by Q in most of the cases. So the complex multiplication where the endomorphism field is CM, these are the special ones. And the ones which are really CM K-theta surfaces are even more special.
How do they move in the modeling?
I'll come to this in a second. Yeah, maybe there's an example or some remarks. If maybe let's do it like this. Yes. So first of all, if S is CM, then the transcendental lattice has to be even. So for K-theta, of course, that's equivalent to have even Picard number. But for Hyperkählers, of course, that's a different condition. So the condition is really about the dimension of the transcendental lattice. That's an easy observation because any CM field has even degree, and hence its dimension, if the dimension of the transcendental lattice is 1, well, actually any vector space over CM field has to have even dimension. Okay, then let's look at the case where the Picard number is 20. So now in principle, there are three cases. It could be real multiplication, and the vector space T could be over the real multiplication field, could be two-dimensional or one-dimensional. or it is a CM. It is a CM. The endomorphism field is a CM field. So that means KS could be real multiplication with the dimension of the transcendental lattice 1 or 2, or CM. And in fact, this part here is excluded. That's an observation by van Gemen. Whenever the endomorphism field is real multiplication, the transcendental lattice has at least dimension 3 over it. And hence, in this case, they are a complex multiplication. In fact, there's also a direct argument. You give me a K-thesis of Picard number 20, then there's a quadratic form in 2 variables on the transcendental part, which is rank 2, and I give a Hodge endomorphism that shows that the endomorphism field is actually a purely imaginary extension of Q, quadratic extension of Q. Okay. That's these examples. Yes, and then maybe to get a feeling for this. So suppose S has complex multiplication, and we are in this slightly weird case where there's a rational class, non-trivial rational class in the plane, in the positive plane. So with PT non-zero, then in fact it is one of those examples where the Picard number is 20. Simply because you take a rational class in here, and then you let act the endomorphism field, but the transcendental lattice of dimension 1 over the endomorphism field, so that will generate the whole thing. But on the other hand, the endomorphism field fixes the positive plane, because that's the 2002 part. So, and that means everything in the full transcendental lattice is contained in here. Okay, so here are a few facts. The first fact is if S is Cm, then S is defined over Q bar. So this goes back to one of the early papers of Piatetsky, Shapiro, Shaffer-Revich. Then also with restriction on the Picard rank, then also to Rijov, and it's also part of a general result which you find in papers by Ulmo and Yafaev. There's a geometric argument.
I have a question.
Mm-hmm.
So is this true for any hyperkähler? This statement?
Which one? This one?
Complex multiplication implies,
Yes. Okay, so for instance, let's geometrically, you can argue as follows. So for instance, suppose the S is maximal Picard rank. Suppose it's not defined over Q bar. Then you spread it out with these 2 line bundles. But whenever you have a family of K-theses, as you said before, the Picard number will jump. But it was 20 generically already, so it cannot jump anymore. That means the family you get by spreading your K-the was actually isotrivial. And that means it was defined over Q bar. And there's a geometric proof also for the other case, if you just assume Cm, by using Buskin's result about the Hodge conjecture, because once you know that, or maybe you write this, you write the Cm field as generated by a primitive element of norm 1, so you have to prove that those exist. And this norm 1 condition means that alpha is actually a Hodge isometry. So it's a Hodge endomorphism plus an isometry. So it respects the symmetric form. And then the result by Buskin tells you this class is actually algebraic. And now you do the same trick with the spread. You spread S and Z, and the Picard number will jump, but the cycle, since it's the algebraic, you can spread it, will continue to act on the transcendental part. But since the Picard number jumps up, the transcendental lattice jumps down, and then there's just not enough place for the class to act on it. So that's a geometric argument for seeing that Cm implies being defined over a number field. Also, you can say, what about the other direction? So suppose you start suppose you start with the K3 surface defined over Q bar, and you assume that now it's not about the endomorphism field, but about the period field, and the period field is algebraic. So you could be interested in those, and then in fact you are automatically in the CM case. So roughly that's the K3 analog of a classical result for elliptic curves. If you have an elliptic curve with algebraic period and being defined over number field, so it's the point in the moduli space is a point with coefficient in Q bar. That's only the case if the elliptic curve, and here the K3 surface, has complex multiplication. Okay, I'm running out of time. There's an interesting question here related to K3 surface defined over Q bar, and if you now take the 2-0 form that is also defined over Q bar and consider the periods of this 2-0 form, then the expectation is that those periods are never algebraic. They're always completely transcendental. As far as I know, this is open for K3 surfaces. Okay, so I should come back to my twistor space. Okay, so back to twistor space. So remember, we started with a K3 surface S and an ample line bundle, so then L was its first Chern class, and we looked at the twistor space as in P1. And we can view, so now this P1 we can view as the Grassmannian of positive oriented planes. So this is planes, this is oriented, and the intersection form has to be positive of the vector space. Now P tensor RL. Okay, so again, P was the positive 2 plane, so that's the real part of the 0, 2, 0, and 0, 2 part. Okay, so that's a 2-dimensional space. I add the ample class L, that's a 3-dimensional space. That's in fact positive definite, and you look at all the all the planes in there, and you give it an orientation. So in a way, somehow you can forget about this P here because everything is positive definite anyway. So how does this identification go? Geometrically, you take a point T here. You take a point T here. So you view this as a complex structure on the fiber, and then it has the 2-0 form. It's a K3 surface on the fiber, and you take its real, the plane that's generated, so it's just the positive plane on the K3 surface ST. Okay. And you can also, so now that's a plane in a 3-dimensional space, so you can also view this as something orthogonal to alpha, and you can normalize the alpha, and so you can see that you get the identification with a sphere S2 naturally by this procedure. Taking the complex structure, the 2-0 form, the plane that is orthogonal to some element, and that gives you an element in S2 after normalization. Okay, so now let's look at the case Picard rank 20. So suppose the Picard rank is 20. So I have this family. Then there are two cases. Either the Picard number of a fiber is 19, and that's the non-algebraic case. So that's not projective. Or it is 20. And then, of course, it is projective, and in fact, it is CM. So what we have in this case, we start with a CMK3 surface, because it's Picard rank 20, and the outcome is also, again, as soon as it is algebraic, a K3 surface with complex multiplication. So rho as equals 20. This implies S is Cm. This implies rho St is 20 if St is algebraic. And this implies St is Cm. I mean, of course, that's a triviality if you want, but it's nevertheless curious to see that an arithmetic property, an arithmetic property of the original K3 surface passes through those highly non-algebraic K3 surfaces to all the other algebraic fibers.
Keep the same field?
Say again?
You keep the same field, or the field?
No. The answer is no, and I'll make this more precise in a second. Okay, so maybe just to dispel one doubt, you could think, okay, I construct this complicated family of K3 surfaces, and then I start with a Cm K3 surface. Maybe all the other algebraic fibers are actually the same K3 surface. In principle, that could happen. So here, that's a little theorem I proved maybe 2 years ago. So if S is Cm, then the set of fibers where St is actually isomorphic to S, unpolarized, is just a finite set. In fact, you can prove more, namely that the set where the fibers are derived equivalent to S is a finite set. And I would even expect, I'm not sure I've checked this really, that the discriminant in the case pk equals 20, so where the Cm field is of degree 2, that the discriminant is, if you bound the discriminant, then there are only finitely many fibers with bounded discriminant. Okay, so now comes the theorem, eventually. So here's the theorem. So we start now with S is Cm K3 surface. So it could be pk number 20, but then the result is
I mean, when you get this twistor family,
yes,
it's a holomorphic map
yes,
to the field map. And so, isn't it obvious that the fiber is finite or just the whole?
No, No, the picture is more complicated. So if you look, first of all, there's like no moduli space, but it's an interesting question. So let's pretend there is a moduli space of complex K3 surfaces, which there's not, okay? Then, so that's a moduli space of all complex K3 surfaces. Then in there, you would think you have the moduli spaces of polarized K3 surfaces of a certain degree, right? And then you start here. And since I use the twistor space that comes with its natural polarization, I get, for each point here, I get the P1, the twistor line, in the moduli space, right? And now this line will intersect plenty of polarized, moduli space of polarized K3 surfaces. That gives you this dense set of where they are algebraic. But in fact, the same MD appears infinitely often in the moduli space. Because when there's a different orthogonal group. Here you divide out by the full orthogonal group, whereas here you only divide out by the orthogonal group of the primitive lattice. And that means the same moduli space MD actually comes up again and again. So there will be infinitely many fibers, usually infinitely many fibers, where the K3 surface has a polarization of the same degree as the original one. But the theorem is strong. It says, but it's never the same K3 surface, the unpolarized K3 surface. That's the. But that's so. I mean, I wanted actually to draw a picture like this in the beginning. So that's why I find twistor spaces so interesting, because somehow it gives you a way to compare different, to relate moduli space for different degrees. There's something we only have in characteristic 0 and not in positive characteristic, but would be very interesting to have things like this in positive characteristic as well. Okay, so now the theorem. So I take a K3 surface, a complex multiplication. I pick an ample class. I look at the twistor space over P1. And now I take a point away from the equator. So maybe one comment on the equator. So S1 is the equator. And I can geometrically describe this as the set of points where the positive plane that comes with the complex surface over this point T contains the ample class L. You see here in the picture, this PT is a plane in here. It could very well happen that L is contained in there. And if you look at all the things that L contains, then that gives you an equator S1. Okay, so if T is not a point on the S1, and ST is algebraic, then ST has CM as well. So in the picture, which is gone, unfortunately, in the picture of my sphere, there was the equator. I don't say anything, well, I can say a few things about the equator, but this theorem is only true for points away from the equator. And I start with the projective K3 surface. As soon as I hit the K3 surface away from the equator, that's also algebraic. The CM property from S will transport to the CM property of ST. Okay. Now I'll come back to Srinivas' question. Moreover, and that is very strange, so their CM fields will be different. That's already the case in pK rank 20, but the maximal totally real field is the same with Ks 0 is Ks ST 0. So here Ks 0 is always the maximal totally real field of Ks. So that's a subfield of degree 2. Well, it's degree 2 in here. So let's try, and then I could finish. Let's try to see what this means geometrically. Remember, I said if I look at the product of S with itself, I look at the Hodge classes in there. The interesting bits are the ones that are define endomorphisms of T, and this one is actually isomorphic to the endomorphism field. And then there's the totally real field here. So in the pK rank 20 case, that will be just Q. And of course, I can identify the cohomology of S times S with the cohomology of ST times ST. You have the same thing. So here now there's the transcendental lattice of the fiber. So that's the endomorphism field of ST. So the first part says if this is CM and T is of dimension 1 over it, then this is CM. And the second part tells you that actually these fields here are the same. So all these fields are natural subfields of C, and as such, these two fields are the same. However, this diagram is certainly not commutative. So this is not commutative. So there is no, in general, you won't be able to drag classes in Ks, so viewed as cohomology class on S times S, along the full twistor space to give you two classes on all the other fibers. So that would be in the sense of the hyperholomorphic bundles. That's not the case. So somehow this part is not here when I'm on the non-projective fiber, but it pops up whenever the fiber is algebraic and not and I'm not over a point in the equator. I have no geometric interpretation for this in terms of classes, deformations. How do I really get a class here to a class over any fiber? But that's what comes out of the Hodge theory.
Sorry, I'm going a little bit fast. Why is H2 of SS equal to H2 of ST?
Because I'm sorry. That's yeah. It's the cohomology identify just H4.
Yeah, H4 is the same.
Yeah. Yes. In the end they are, but that's not automatic. Okay, maybe that's a good point to stop. Thank you.
So if you take a Keter surface with a rho equal 20, and so it is a CM, I believe that it must be a Kummer surface of a product of
right.
elliptic curve with CM.
Up to maybe degree 2 map or something.
One self-product.
Yeah.
So
yes.
The case.
And then so a CM translates. So whenever you have an abelian surface and look at its Kummer, the abelian surface is CM if and only if the Kummer is CM. I mean, essentially the transcendental lattice is the same of the two.
Other questions?
I mean, in this diagram, you have, I'm thinking about the Hodge conjecture. So, I mean, what is, how much bigger is the H to 2 with coefficients in Q with respect to Ks?
It's the same. So what is missing? So these two parts, they have the same. Since they are CM, this is the same dimension here, and the complement is the endomorphism of the Néron-Severi, and the Néron-Severi is, because I'm away from the equator, this has the same Picard number. So the size-wise they are just the same, even the two parts. But the interesting part is really in the transcendental part.